Dr. Kaoutar El Maghraoui is a principal research scientist at IBM Watson Research Center, where she is focusing on innovation at the intersection of system and artificial intelligence. She leads the experimental AI testbed of IBM Research AI Hardware Center, a global research hub focusing on enabling next-generation accelerators and systems for AI workloads. She is responsible for the open source development and cloud and user experience for digital and analog AI accelerators at IBM Research. In 2017, she co-led IBM Global Technology Outlook, a key internal strategy effort, where she contributed to create IBM Vision for the future of IT across global labs and business units, focusing on IBM AI leadership. Kaoutar has co-authored several patents, conference, and journal publications in the area of system research, distributed system, high-performance computing, and AI. Kaoutar holds a PhD degree from Rensselaer Polytechnic Institute, USA. She received several awards, including the Robert McNaughton Award for Best Thesis in Computer Science, Best IBM Award in 2021, IBM Eminence and Excellence Award for Leadership in increasing women presence in science and technology, several IBM Outstanding Technical Accomplishments, 2021 IEEE TCSVC Women in Service Computing Award, and 2022 IBM Technical Corporate Award. Kaoutar is the Global Vice Chair of the Arab Women in Computing Organization and avid supporter and active member in many Women in Science and Technology initiative. Thanks, Kaoutar, for your time and your presence. The floor is yours.
Thank you so much, Danilo, for this introduction. It is really my great pleasure to be here with you today and to give you a taste of what's next in AI hardware acceleration at IBM Research and how we're trying to power the next era of accelerated AI computing. So first, I would like to acknowledge the team behind this work. So this is a large and big collaborative effort at IBM Research. And I mentioned some names here, but there are other contributors that I just don't have the space to include. So thank you. I would like to thank all of them. So this is the outline for my talk today. So first, I'm going to give an overview of our roadmap for accelerated AI in the AI Hardware Center and give a quick overview of analog AI. Then I'll talk about our open source efforts in analog AI hardware acceleration. Then I'll talk about, our web interface and interactive experience. If I have time, I'll show a quick demo and then I'll leave the floor for a Q&A. So first, why this is important. AI and especially deep learning have achieved incredible performance, as we all know, in numerous fields, including computer vision, speech recognition, NLP. However, with this huge success also comes increased complexity. The first thing here that we see is deep learning models are getting larger and deeper with millions and even billions of parameters. In fact, the number of DL models increasing, the number of parameters in deep learning models increasing in the order of 10x year on year. The other trend that we see here is that with this increased complexity, this also comes with translates into high computational demands. In fact, what we're observing here is the compute requirements for AI, training large AI jobs has been doubling every 3.5 months. And most of these models are very expensive to computationally run on devices like, tinyML devices, embedded devices, edge devices. And of course, the most important here is that with all of these increasing computational demands and also comes the increased carbon footprint. And, we see here an example that was mentioned at the university by the University of MIT, Massachusetts, Amherst, that training a single model can emit as much carbon as 5 cars in their lifetime. So with all these challenges, we've seen, the potential of AI to stream more and more tasks. But, to satisfy this AI's thirst for energy and ever increasing complexity, we need to keep developing efficient AI hardware. And this is what motivates IBM to create, this AI hardware center, which is a cross-industry ecosystem and effort with several industrial and academic partners with the mission of innovating and enabling next generation chips and systems to support this tremendous power and unprecedented speed that AI requires. And of course, we're here talking about tinyML and on-device learning. These are some of the key enablers, for on-device learning. So what we need to do to get to efficient and faster AI. So we have this roadmap that would enable us a path to 1000x improvements in the next decade. So we're looking at a suite of techniques that can improve the efficiency of specialized digital hardware accelerators geared towards deep learning, inference, and training. And our research team has published extensively on the use of approximate computing techniques, specifically the use of reduced precision computations to design and build optimized deep learning hardware. There's also a considerable effort that is spent on exploring technologies that can continue the performance demands of deep learning once the digital solutions are exhausted. And these efforts, they were coming back, to a computation technique that has long been forgotten, which is analog computing. And in this talk, I'll talk more about what we're doing in this space. And in addition, IBM is also leading in quantum computing, and we're looking on quantum algorithms that will advance AI. Specifically, we explore quantum algorithms that will be able to tackle large problems that are far beyond reach for classical computers. So what I'm showing here is our AI hardware center roadmap for what's beyond the GPU. So the question we're trying to address here is, what technologies do we need to develop and advance to continue this rate of progress and go beyond the GPUs? So the AI Hardware Center was launched in 2019, and we proposed this roadmap with a 2.5x annual improvement in AI compute efficiency over a decade. Approximate computing techniques are at the heart of this. Initially, applied to reduce precision digital AI cores, and then next, is the analog computing that will be key to continue this trend of progress here. So fast forward, to today, we continue to exceed our roadmap of 2.5 times annual improvement in AI hardware compute efficiency. For example, our recent results of the third generation of the reduced precision digital AI cores that we published at ISSCC conference in 2021, they show that we doubled our performance efficiency projection for training and outperformed our roadmap projection for inference by 6-fold. And in today's talk, I will focus on the work that we're doing in analog AI, and especially around, the tooling and the user experience that we're providing to allow the community to be able also to experiment with this next generation technology. So first, let me just talk about what do we mean by analog AI, especially for the participants in the audience that are not familiar with this. So non-volatile memory, or NVM, technology enables in-memory computing, which eliminates the Van Neumann bottleneck and allows performing computations directly in memory. And this is done by mapping neural networks to analog hardware and storing the neural network weights as a property of the non-volatile memory material itself. So this, what it accomplishes, it eliminates data movement altogether. And this AI approach can offer unparalleled speed up and also energy efficiency for AI workloads. So I'll touch briefly how this is done conceptually. If you look at the building blocks of deep learning, so we have these multiply, accumulate operations. We also have the update that we have to do in the backward pass. And then we have the activations. So matrix manipulations and these nonlinear activations are reoccurring operations in deep learning networks. And if we look deeper into this, we see that the general matrix multiplications are the dominant operations in many of the neural networks. Here we have done these performance characterizations across a wide range of neural networks across various modalities like speech, language, and vision. You can see that the majority of the operations are dominated by these GEM, or general matrix multiplications. And this is what analog AI is trying to accelerate. So let us look first at how this is done conceptually. So if we look at analog in-memory computing and how it is bringing efficiency, digital accelerators are typically set up like this, with the processor on one side and the memory on the other side, and they're connected through a bus. So let's say you want to multiply two numbers, A and B, and so initially they start by sitting somewhere in memory, but they need to be sent to the processor through the bus. And the answer is computed and then sent back to the memory again through the bus. And this is fundamentally what consumes most of the energy through this data movement. Additionally, this bus can be a source of bottlenecks, especially if you're doing a lot of data movement, a lot of computation, and this is what we see in neural network computations. Analog computations, on the other hand, get rid of this processor on this side and do everything in memory. And so how this is accomplished, this is done by storing A as a property of the memory itself and sending B as a voltage. Basically, the computation is done instantly in the memory itself. And this eliminates this movement, which drives a lot of energy efficiency. So let's look how this is mapped, how typically a neural network is mapped into memory and how the multiplications is performed. Let's look first at, how the dot product that is really key as part of the analog, the neural network computations is accomplished in analog. This is, just going over some of the basics physics for the people who are not familiar with this. What I'm showing here is, consider a simple circuit where you have 3 wires and then 2 resistors, shown here in red. And these 2 resistors have conductance values, G1 and G2. So if I apply a voltage V1 and V2 across these 2 wires, the first wire injects a current that is calculated by I1 equal V1 times G1, and the second wire injects a current calculated by V2 times G2. So these currents are accumulated towards the end, and the resulting current is I1 plus I2, which is actually V1 times G1 plus V2 times G2. So that's what we're doing here is relying on Ohm's law and Kirchhoff's law, which does this accumulation, to perform the multiplications and additions in the analog domain. We can extend this concept further and create a dense grid of resistances, which can be programmed beforehand. And this gives us a matrix of conductances G and I. And when I apply a vector of voltages, V as input, the current in each vertical line is a dot product of the input voltage and the vector of program or residence conductances G. So the current coming out are the result of a vector matrix multiplications. And this grid of resistance is what we refer to as an analog crossbar array. So here we're just showing, using the magic of physics, we can do this vector matrix multiplications instantly in analog domain. So, so if we want to see how this is done, how we are mapping actually a neural network and how we're mapping computations from an input X, from an upstream neuron to a downstream neuron Y, a vector matrix multiplications operation first multiplies each element in an X vector with the corresponding weights. Then the multiplication results are summed over all the elements. And F is a nonlinear activation function that is required, to ensure that all these different layers in the neural network don't efficiently become another linear layer. So this is basically just the basics of neural network computations. And we just see here that how these things are mapped. So each weight is then mapped into 2 devices in this crossbar array. And typically there are, 2 conductances, G plus and G minus, to be able to represent negative and positive weight values. And then to do the multiplications, we either send an analog voltage or a digital voltage with analog duration to this crossbar array. And because of Ohm's law, each memory device will conduct this instantaneous current or accumulated charge over time that is proportional to the weight W and the input X. And basically, this sum is performed using Kirchhoff's laws that I mentioned before. And we can see here, analog computing is quite magical. I provide the inputs on the left, and in parallel, several neurons are doing all the necessary math with this natural summations of the currents. So what we have, seen so far is how an analog engine performs this dot product computations, which is the bulk of the computations in deep neural networks, as I've shown. However, analog units are not always precise, and they require, high overhead of analog to digital conversions. And for many reasons, the analog values need to be converted to digital values. For example, for buffering the results, for sending them over long wires, for doing pre-processing, for preventing errors, and so on. So this conversion is done typically using analog to digital converters, which is a non-trivial circuit with high power and area overhead. And which makes, basically designing a chip, an analog AI chip, not a trivial task. So what I'm showing here is an example implementation of a crossbar array using phase change memory technology. So each BCM material is sandwiched between these two overlapping vertical wires on the two metal layers. And sometimes, these elements that you see here, these cross points, we call them resistive processing units or RPU cells. And an in-memory computing chip consists of multiple crossbar arrays, these crossbar arrays that I'm showing here, and of memory devices that communicate with each other. And the neural network layer can be implemented on at least one crossbar array, in which the weights of that layer are stored in the charge or conductance states of the memory devices that these cross memory points represent. So as I mentioned, so this is just shows at a very high level how this is done conceptually. And I show here an example using phase change memory. So as I mentioned, analog units are not always precise. They require high overhead. And, that's why, there are also multiple options. There is no ideal device actually for analog computing and many promising candidates. So for instance, phase change memory, has is a mature among the storage class memory, but it also has these disadvantages here shown highlighted in red. It has this abrupt reset behavior. It is not symmetric, and it also suffers from drifts. The values that you program, these conductance values, they drift over time. There is also random resistance random access memory, electrochemical access memory, CMOS, magnetic RAM, FRAM, photonics, and so on. And this is not by no means a complete list of possible resistance elements, but examples of how analog resistance levels are achieved with various materials and circuit implementations. So for instance, phase change memory switches between a highly resistive amorphous state and the more conductive crystalline states. And depending on the shape of the crystallized volume and the level of crystallization, this intermediate resistance between the fully set and the fully reset states can be achieved. And this is how we're representing these weight values. And to be able to achieve an analog in-memory chip, there are various requirements that need to be satisfied in the material or devices that we use in these crossbar arrays. For inference, forward inference, and training, they have different needs and requirements. For example, in forward inference, we deal with fixed weights. In training, we have these frequent weight updates that you have to keep doing during the training process. So for inference, materials need to have these properties: long-term retention of the values because the weights are stationary, excellent conductance capability, modest endurance, and modest programming speed. However, training, we need to have modest retention, high endurance, fast programming state because we have to do multiple updates, and this gradual conductance change. And the path to ideal analog compute material or in-memory chip. So what we have shown is we need to rely on a lot of algorithmic boosters. For instance, hardware-aware retraining to be able to achieve ISO-accurate analog AI inference compared to what you would get in digital chips. So, and these algorithms are needed to incorporate analog deficiencies and non-idealities such as noise, circuit offsets, the ADC and the AC resolutions, etc., in the forward training pass. And retraining also in hardware-aware manner increases the robustness of these neural networks when you're doing inference on the analog memory itself. And also to achieve near ISO accurate inference performance, using these techniques, we have shown, as shown here in this figure on the top right, that with these techniques, we're able to achieve almost near ISO accuracy. For example, for the NLP task using BERT-based on GLUE, and the average, you can see here, accuracy on analog AI was 80.10 compared to what you would get in digital hardware, 80.70 is almost close. And all of this was achieved because of these algorithmic boosters. So what I have shown is just a glimpse of some of the innovations that AI is driving in hardware. Because of this, this has motivated us to open source the IBM AI Hardware Acceleration Kit, which is a new and first of a kind open source toolkit that uses the PyTorch framework with full GPU support, and it provides a suite of tools that enable one to master and accelerate analog hardware technology for more sustainable AI models. And so the toolkit basically provides you a way to understand, explore, experiment with various materials, but also with various algorithms. And it also have access to the open source analog libraries that our team has developed, and to be able to experiment with them in the context of your workloads and data sets. So I'll talk a little bit about, what this toolkit provides. But in addition to this simulation framework that we have created, our team is also building real analog AI inference hardware. And there's also work on analog AI training hardware also. And these are first of kind industrial demonstrations of analog AI hardware. So for the first time, IBM Research announced at the VLSI in 2021, a 14 nanometer fully on hardware deep learning inference technology that was used in two types of analog AI compute chips based on phase change memory. And this is basically the two demonstrations that we had to date, and there is more that we're working and will announce soon in upcoming conferences. So the first one here is we've demonstrated a 1 and 2 layer MLP using the MNIST data sets for image recognition, and the other hardware demonstration used ResNet 9, a CNN network on CIFAR 10, also for another image recognition. And here, I put references to the papers that detail these demonstrations and the technology behind them. Both of them were presented at VLSI 2022. So next, I will talk about the analog hardware acceleration kit and what this platform allows in the context of analog AI. So when we're looking at analog AI accelerators for neural networks, we assume that for a given AI workload, such as CNNs, convolution networks, the weight matrices are situated on the analog crossbar arrays. And I talked about what an analog crossbar array is. And the matrix vector product is accelerated with analog in-memory operations. So here we consider two possible accelerators, one that targets neural network training and another one that targets neural network inference. So to accelerate training of neural networks, the accelerators need to implement the forward and backward pass, both of them, and update passes necessary to do the computations of the stochastic gradient descent. However, the accelerator is only targeting inference, then a pre-trained model is programmed on the analog chip, and only the inference part is accelerated, meaning the forward pass. So we further assume here that only the matrix vector operations are accelerated in analog, and those are, like I showed, the dominant operations in neural networks. So these latter, they're done in the digital domain. The other, operations like nonlinear activation functions or pooling functions, we do them here in digital. And we also assume that we will separate digital compute units available on the same chip. So to be able to do these digital coprocessors along with the analog in-memory compute processors, the activations need to be converted to analog for each crossbar array. And that's why we use these DAC and DAC converters to be able to basically do this communication between the layers. And there also could be additional digital pre and post processing like activation, scaling, or bias correction, which will be done in floating point or digital as well. So this just shows in our simulations what are the pieces that we are doing purely in analog and the other pieces that we have to rely on digital technology. So why this is interesting, why analog AI acceleration is interesting, and why computation in analog is interesting for AI acceleration. Let me reiterate some of the advantages and the challenges here. So first, due to this parallel in-memory compute, the matrix vector product is very power efficient as the weights are, the weights data does not need to be fetched from memory for each operation. And the second thing, because the analog matrix vector product is performed using the law of electrophysics, it is also computed in constant time. So what this implies is a large weight matrix needs in first approximations the same time that the smaller weight matrix has. And that's not the case. This is what's shown here in red. That's not the case if you do this in digital hardware. The time to do the computations for larger matrices is much higher than for smaller matrices. Because the time, to compute the matrix vector product typically scales with the number of matrix elements. And with all these great advantages, we also have a lot of challenges for analog AI computing and accelerators. Most importantly here, the analog vector product is not exact. There are many possible noise sources and non-idealities. For instance, as shown here in this graph, repeating the same matrix vector product twice will result in slightly different results and outcomes. And this is the main motivation behind developing this flexible simulation tool for analog acceleration, which allows you to investigate whether you can achieve acceptable accuracies when we accelerate important workloads, and what are the algorithmic things that you have to do to be able to mitigate this noise. So there are basically a lot of noise sources, but that's why we need to develop new algorithms and error compensation methods to improve the accuracy and reduce the potential impact of this expected non-idealities of the analog AI accelerators. So, and to engage, the community in this endeavor, we, as I mentioned, we have open sourced our simulator. And we hope that we engage the wider, AI community, also the tinyML community, to help us optimize algorithms and DNN technologies for further analog AI hardware accelerators. Of course, with this technology, you could build accelerators for data centers, but you could build accelerators for edge and tinyML devices. And the design, of course, will be different. The challenges will be different in each one of those cases. So with that, let me talk about, what we have in this toolkit. So the simulation toolkit, the key focus here is on the algorithmic and functional levels as opposed to the hardware and circuit design levels. So this simulation toolkit can be used to estimate the accuracy of a neural network mapped to an analog crossbar array. And you can also experiment with multiple materials and devices. And also the toolkit considers both analog inference and training, and uses the flexibility of the PyTorch framework, deep learning framework. We also follow modern open source standards, such as maintaining a GitHub repo with an issue tracker, unit testing, examples, documentation, and so on. And you can easily install this by simply using pip install and the AI hardware kits. So this shows the code structure here, a brief overview of the code structure. So neural network is simply defined using layer modules in what you would typically use in PyTorch. And to build analog components into the DNN, we provide these additional layers that encapsulate the analog computations using an analog tile. So we provide several modules to flexibly build CNNs and other, not just CNNs, we also have LSTMs and other types of neural networks that we're supporting for recurrence, for example, here. And each analog module is based on a highly configurable analog tile, which represents the characteristics of the hardware and simulates the forward, backward, and update behavior. And these tiles can be configured with RPU configs. We call them resistive processing unit configurations. In other words, these are constructs that allow you to configure these tiles to different hardware configurations, such as material choices. As I showed, there are multiple material choices that you could choose from. Even the pulse response, when you apply voltages, the response of the material will differ depending on the type of the memristic elements that you're using. And here, the simulation engine is written in C++, and we use Python bindings to communicate with the PyTorch interface. And we also have highly optimized the simulation of the analog compute using custom written CUDA kernels on GPUs to accelerate the simulation. Here just shows, some of the examples we have. We have a lot of examples, simply in Python, but also in Jupyter notebooks that you can run directly in Google Colabs that illustrate the functionality for both training and inference. And there is extensive documentation and API reference using the Python Sphinx framework. This just shows an example of how you could use this toolkit to train a small network. So first, what you do is you define an RPU configuration, which basically specifies the hardware that you want to simulate. In this case here, we're using resistive random access memory. It's a preset, or think of it as a template that we provide, or a preset that was fitted to experimental data that we have measured from ReRAM memory. And in this case, incremental updates of the conductances will be very noisy in this material. So we define a neural network just simply as you would do in PyTorch. And here, notice the difference that we have these wrappers, analog linear as opposed to linear. And then we define a network that contains analog. This will define the network that will contain analog that will be mapped to analog tiles. And after the network definition, you define an optimizer. And here the optimizer can be chosen, which is only used for the digital parameters, or optimizer that are analog specific. And then at the end, here you can see that after the network definition, choosing the optimizer, the specifics of the update of the analog tile are defined in this RPU configuration. Here I just show a simple network, but there are a lot of more parameters that you can adjust. And here at the end of the training loop, we use the standard PyTorch syntax. The forward pass is called, then the loss is evaluated, the backward pass is called, and then finally the optimizer is called. So it's very simple, not a lot of changes in your typical neural network to be able to include these analog simulation behavior. And since we want to be able to scale this simulation to relevant neural network sizes, big and small, to have the full range, it's really not feasible to simulate the physical system in great detail. So that's why we're focusing on functional simulation. And here we use an abstract way to represent only the effective noise sources and then non-idealities of the analog hardware. And we can define different noise sources and strengths, and also the value of the range of the input also can be quantized because of the physical limitation details of the hardware. So there is a lot of capabilities here in terms of limiting the range, limited ranges and quantization, the different weight noise types, the dynamic input and output scaling, and so on. And for the training, there are lots of algorithms that we have implemented. There was a lot of work spent, to develop these algorithms to be able to estimate the impact of the noise characteristics of different material choices such as the asymmetric resistive device update behavior or the device-to-device variability. So these algorithms, they're all published, in top conferences and journals. And I don't have time to go in details over some of these algorithms, but I invite you to explore these papers offline. So for example, we have implemented 3 different ways to perform the update in analog and hope to extend these number of optimizers, available optimizers in the future. This is something that we're currently working on. So the first optimizer, called plain SGD, it implements the fast way to do the gradient update fully in analog using coincidences of stochastic pulse trains to compute this outer product that are as suggested, by the paper here. And the second optimizer, what it does, it's called mixed precision, because some of the computations are done in analog and others are done in digital. And here, so in this case, the outer product to form the weight gradients is computed in digital compared to the first optimizer. And this would be a good choice for more non-ideal devices. If you have a material that has high noise ratio, it would be good to design a chip that has pieces done in digital and pieces done in analog, like this algorithm proposes. And the third optimizer, called tiki-taka, it implements an algorithm that is similar to momentum, stochastic gradient descent, and assumes here that both the momentum term and the weight matrix are on analog. And the gradient update computations will be using the same fast update as in the first algorithms. As I mentioned, I don't have the time to go into details, but I just want you to give you a flavor.
Please. Sorry, apologize to interrupt you, Kaoutar. You are running out of time. If you could kindly wrap up, please.
Sure. So let me just go quickly to the inference. In inference, as I mentioned, hardware-aware training is really key to be able to achieve robust inference on analog hardware. And we also have a lot of techniques here that we have implemented where we do the inject the noise in the forward pass, where we simulate these analog non-idealities. And then the backward path is done perfectly as in digital. So during inference, there are all these challenges like cycle-to-cycle noise, programming noise, drift, and so on. So hardware-aware training is the technique that we use to add noise during the training. We do also weight clipping and then training of output scales, and this allows a robust performance. I mean, here I'll skip this, just shows an example how we would use hardware-aware training for inference. And I'll just, quickly go to talk about our interactive experience, which we call the Web Composer, which is a cloud-based simulation that allow you to access the same, all these functionalities that we have open sourced in an interactive way. So this is a no-code experience where we have pre-configured analog device presets, where we also give access to all these algorithmic advances, and you have seamless interactions with the open source toolkit. And we're also, so far we have inference and training, and then we're working to also augment this interactive experience with access to our real hardware chips, starting with our IBM Zurich Fusion chip. So I post here the URL in case you're interested in exploring this. And I don't know if I have time to show a quick demo, or we should just jump into the...
Yes, please go to the conclusion, Kaoutar. I'm sorry, but...
no problem.
The time passed.
So basically, to conclude, I just wanted to highlight the importance of all the algorithmic work that you have to do to be able to achieve ISO accuracy on these next generation accelerators that leverage analog. And analog AI has a lot of promise in terms of providing energy efficiency, which are basically key enablers for tinyML and on-device learning. I'm going to stop here to see if there are any questions.
Thanks a lot, Kaoutar. It was a great presentation and full of information that would need further deepening. There are a couple of questions. Unfortunately, really we are out of time. So I invite you kindly to address these two questions, which are on the Q&A chat. And I invite you also to stay with us for the remaining two presentations. Please type in your answers. There are two questions. I think these are quite easy for you to address.
Okay,
thank you so much, Kaoutar. Thank you. It was much appreciated your presence. That forum was possible thanks to the tinyML Foundation support and all the support from the strategic customer, which are helping a lot in providing resources to make sure that this forum and other events and other interesting events will happen in the future. So just to thanks also and list the executive strategic partners: ARM, Edge Impulse, Qualcomm Research, Sentient, and the Platinum Strategic Partners: DeepLight, Clickattack, Reality AI, Renesas, Sony Semiconductor. The Gold Strategic Partners: Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, Sensimil, ST Microelectronics, Synaptics, ScienceSense, and all the silver strategic partners. Thanks again to stay with us yesterday and today, and I hope it was a valuable experience. Thanks and see you soon. Bye.